So this is the
No, sir.
free particle propagator. Okay, so okay. So as the last topic from path integral, I want to cover something very fun. It's called the Aharonov-Bohm effect. And it's an effect which is very, it's related to some deep physics in quantum field theory, but you know, but that's separate. But this has to do with the way that a charged particle, an electron in our case, interacts with a magnetic field. Okay. So to be able to do that, we first need to understand how to include, we have to formulate quantum mechanics of a charged particle in a background electromagnetic field. So in a background, sorry. So what do I mean when I say a background electromagnetic field? What I mean is that we are going to treat the field as a classical field in which we have a charged quantum particle, okay? So here we are not treating the background field as a quantum mechanical entity. Quantum mechanics is not powerful enough to deal with the background field as a quantum mechanical entity. For that, one needs quantum field theory. However, even in quantum field theory, the treatment of the Bohm-Aharonov effect, I think, can only be done semi-classically. Okay, so before I can tell you about the Bohm-Aharonov effect or the Aharonov-Bohm effect, I want to introduce the notion of how to couple a particle, a quantum particle, to a background field, okay? So I have to do a little bit of a detour and talk about Maxwell's equations. Is that all right?
Yes, sir.
So I think this is going to be fun. How many of you have not seen Maxwell's equations? Is there anyone who hasn't seen Maxwell's equations in its differential form? Okay, you have all. Okay, so my next topic is going to be Maxwell's equations and the gauge potentials. Okay, so I'm going to introduce a new idea called gauge potentials. They're also known as a vector potential. Okay, so you know from electrostatics that the electric field, given an electric field, you can define an electric potential, which is the gradient of the electric potential, right? Because of electrostatics, you can do that, right? And why is that? Because in electrostatics, the curl of E is 0, right? So because the curl of E is 0, from vector calculus, you know that the curl of the gradient of anything, any function, is 0, right? And because of that, this allows us to express the electric field as the gradient of a scalar function called the potential. Okay, are you guys familiar with the idea of a potential? You are, right? You saw that in second physics 112, for example. Okay?
Yes, sir. Yeah.
So, but I guess what you were not, did you guys take electrodynamics? Have you, some of you taken electrodynamics?
Yes, CED.
Okay. So you know that, this curl of grad being 0 is the real reason why you can express the electric field as a gradient, right? Because then, so what we are doing by defining the gradient is that we are trading in, a variable with 3 degrees of freedom per point in space-time, the electric field. We are trading that in for a function which has only 1 degree of freedom, so to speak, at every point in space-time, right? But we are not losing anything because we can get one from the other. We can go this way by doing differentiation. We can go this way by doing integration, right? This is the wonderful thing about calculus, is that because we are working with continuous objects, we can work with something simpler. So similarly, you know that the divergence of the magnetic field is 0, right? This is saying that there is no magnetic monopole, right? That is what this equation is saying. Because if I look at the analogous equation from electrostatics, it's going to give me the charge density on the right-hand side. So because we do see electric charges, therefore on the right-hand side of this equation, it is not in general 0, but this is 0 because we have not seen any magnetic monopoles. If we see a magnetic monopole, then we'll have to amend this equation. But so far, we haven't seen any magnetic monopole directly. So that if we have a divergence of a vector quantity, then we can always write that vector quantity as a curl of another vector quantity. From vector calculus, you can show very easily that the divergence of curl of any vector quantity is 0. Okay. So this equation allows us to define a new potential that we call the vector potential. Okay. A is the vector potential. So it is a kind of a magnetic potential, okay? Are you guys following so far?
Yes, sir.
Okay. So what we have done is that we started with Maxwell's equation, where our fundamental variables were E and B, and they of course depend on both space and time points, because in general, they depend. We are not just dealing with electrostatics. And then what we do is that we are going to trade them in. So I'm using a notation from chemistry. We are going to trade them in for four variables: the electric potential and the magnetic vector potential. So you know that Maxwell's equations are actually invariant under Lorentz transformation of special relativity, right? Because Einstein was inspired to formulate special relativity because he realized that the symmetry of Maxwell's equations is not the symmetry of Newton's equation. And it's the symmetry of Minkowski's space, which is the symmetry of Maxwell's equation. So he was willing to discard Newtonian physics for Minkowski geometry, or Euclidean geometry for Minkowski geometry. So I'm not going to do that, but if you do a covariant formulation of electrodynamics, then we combine these four components to a four-dimensional vector potential whose zeroth component is given by phi, and the three spatial components are given by A. There's some factor of CM stuff that I'm not going to write down here. Okay, so this is, I'm just telling you this so that you know. It's not essential for our discussion. Okay, so how are E and B related to phi and A in general? It's because you have seen phi more in the electrostatic setting, but of course it is should also be relevant in the dynamical setting. So if you look at the dynamical setting, then the electric field is given by minus gradient of phi minus 1 over c. The c is there for dimensional reason. The time derivative, the partial derivative of A. Okay. Of course, if it's a static situation, then this guy goes to 0. And B doesn't change. B is the same as curl of A. So these are the equations that relate the electromagnetic field to the vector potential, to the electromagnetic potential. Okay. So these are essentially A and phi are essentially new. These are new actors whose roles are equivalent to E and B.